I guess I'll wait for everybody to get seated, just relax. But yeah, thank you all for allowing me to speak today. It's a pleasure to be here in Tampere. Actually, Tampere was the first city I came to in Finland after I completed my PhD. I did a postdoc here with the host, Matti Manttusalo. And then I moved up to Oulu in northern Finland. So but today we're gonna, you spoke about my title already. We're gonna look at some technical challenges related to roll-to-roll processing of these double-sided systems and more of a large area and manufacturing approach compared to a little bit different from some of the talks we saw earlier today. But just to give a little brief, who here has heard of VTT before? Oh, just a few of you. I'm very happy to give you a nice little introduction. No, I won't dwell on the introduction too long, but we are the Technical Research Center of Finland, the equivalent of, let's say, a TNO for the Netherlands or Fraunhofer in Germany. VTT, though, it's a private company. It's owned by the government, and only about 30% of the funding comes directly from the government or the state funding. The rest comes from public funding, as well as customer projects. So I was mentioning that I come from up here in Oulu. So I moved from Tampere to Oulu after my postdoc, and this is where we have our roll-to-roll printing lines. The headquarters of VTT, it's down here in a city called Espoo, but really it's what that is it's just a suburb or a city outside of Helsinki, but really it's Helsinki. Helsinki is comprised of Espoo, Helsinki, and Vantaa, where the airport is. But anyways, Oulu is quite beautiful up in northern Finland on the Gulf of Bothnia. And really the goal for VTT, though, started in 1942. Our goal is to work for customers within Finland and globally to help technological advances. Today, we're going to look at a little bit of what the type of, you're going to get a good feel of the type of roll-to-roll processing we do at VTT, how it influences some sectors like health and well-being. Of course, we're always considering sustainability. And my background is actually in thin film photovoltaics, specifically organic photovoltaics. But now a lot of work we're doing now is on these perovskite thin films. And the particular investigation that I want to share with you is related to this double-sided system production. So we do this roll-to-roll laser cutting. We fill with rotary screen printing of different conductive pastes, and we could do this on just plain PET, but also PET with conductive. Transparent conductors, on both sides or on single sides. And then there's a use case I want to show you at the end, which I'm pretty excited about, is these OPV and perovskite photovoltaic energy modules. So at VTT, we have these three different business areas related to carbon neutral solutions, digital technologies, and sustainable products and materials. The printed electronics domain is under the digital technologies. And what I was saying earlier is there's this bridge between academia and industry that VTT fills. So a lot of the talks we saw earlier today are really academic and beautiful research with lower TRL. And then what to do next? How to bring those ideas that we saw you all speaking about to market. We need to scale them up. You need to productize them, and you need to have good business models. So that's where VTT fits in. And at VTT, we do a lot of work with we have several different pilot lines. We're going to look at a few in detail that relate to the particular paper that I'm talking about today. But in general, we do have all the capabilities for printing on flexible and stretchable substrates, both in sheet and roll-to-roll. We also do assembly and interconnection of the components, and then there's also post-processing. We do everything from there's a full converting line with robotic arms, but we also do injection overmolding for something called structural electronics. There was a spin-off company called Taktotech, a spin-off from VTT, and they're also up in Oulu, and they work a lot, for instance, in the automotive industry, reducing material use in a lot of the automotive electronics. So what you do is you take your hybrid system, so traditional electronics on a printed backplane, and then you overmold it in plastic to give it a structural element. So you're really reducing basically the material use, and they're doing a beautiful job there. So where did they come from and why did they start there? That's just one use case, for example. But at VTT, we really put a lot of emphasis on this development back in the late 1990s. Heavy investment throughout the 2000s, and a lot of and in basically in about 10 years ago was another big investment for the larger roll-to-roll lines at VTT. I'm going to speak a little bit, but just one use case some of the wearable electronic development we do. So we do from design to manufacturing. Pilot manufacturing. We're talking thousands of units, even tens of thousands of units. This is when companies want to reduce their risk. It's not too much. It's one comment of silver or urethane, and then you can place through the functionality of the device. You're not just relying on digital electronics. And then you propose it to them. You have so for those of you who haven't heard about VTT, I hope at least this video, people like visual messages often. So hopefully at least now you remember our logo and you can make, oh yes, I remember that. They do some work with roll-to-roll processed electronics. But let's see. You can tell your colleagues about it, please. I talked briefly about sustainability. So there's a big influence on sustainable product development, sustainable life cycle of products. You don't need biodegradable electronics to make your product sustainable. That's not the point. But I just want to show a little bit of flavor here to see that you can. Some work that we do is look at a little bit more sustainable materials, maybe from the environment, from nature, or derived from nature, like this nanocellulose films that are biodegradable. And this is an example of one of these health monitoring patches that can be made on these substrates. We've also done some work with these thin film photovoltaics on these biodegradable substrates. Some people might be saying, well, why do you want biodegradable substrates? It's just going to deteriorate. Don't you want to increase the lifetime? Well, in most cases you do, but sometimes, for instance, in like agro electronics, where you might put the electronics in the environment with plants to monitor, food crops, you don't want to have to go pick up all the electronics later on. So one idea is that maybe you can develop more friendly environments that can go into the be absorbed into the dirt. Of course, you don't want to use. Obviously you're pointing out there's ICs there. You don't want to leave those around. So we're not quite there yet, but on the way, I think. Now my background is with these photovoltaic manufacturing. So what we do here is we're printing multiple layered devices. Often we'll have the conductive transparent oxide, and then you'll have like an electron transport layer and an active layer, then maybe a hole transport layer, followed by your back contact electrode. And for integration, this is where we get more into the depth of the case study that I want to discuss today, is where we have these different laser options to either after post process you can access the devices if they've been encapsulated, or in this case you can use a CO2 laser. Here's two examples from work that we published relatively recently. But you can use these double-sided vias for, let's say, doing those health monitoring patches. You can have the electrode on one side, and on the other side of the substrate you have your electronics. Here's a paper I published with Matti Mantusalo. This was for sheet-based processing. We used a UV laser on our roll-to-roll lasering line, and we just did sheet-based screen printing. But then the question is how to go to volume manufacturing. And so this is where it comes into a little bit more complicated, because there's many steps to get to this double-sided system. And this is just for the double-sided printed silver, or the FPC. So the first step we always do when we're doing roll-to-roll processing is the thermal pretreatment. Even though we get our substrates, for instance, this Melanex ST506 that's heat stabilized, when you're putting it under tension on a printing line and around 80 newtons of tension, and it goes through the thermal the thermal ovens, there's a small percentage of stretching. But one good thing is once you do a thermal pretreatment at that particular condition, if that's the most extreme condition that substrate's going to see in the roll-to-roll process, it's not going to stretch any further after that. That's something we proved in this paper that I published recently in the International Journal of Advanced Manufacturing. So after that's done, then if you have of course, ITO on your substrate, you'll want to do ITO etching. We do wet etching at VTT. And then when we want to do these vias for the double-sided systems, we use our roll-to-roll CO2 laser line. And then we also add a PET liner. This is done on this converting line up in Oulu. And this is our CO2 laser is right here. The reason why you want to add the liner is so that you don't get any fouling or ink seepage through the via holes. Of course, when you're doing sheet-based processing, you don't really think about this, but when you're using roll-to-roll processes, it's very important to consider these. So after you add the liner, then you can go to your printing line. This is one of our larger roll-to-roll printing lines. And here you can see, well, the printing unit would be on this far end, and then we have these large ovens that are spaced out sequentially. The reason why it's 2 stories is so that we can reduce basically the surface area of the device. If not, it would be outside the building. After printing on one side, then you can remove the carrier foil back on the converting line. You can add another carrier foil on the opposite side where you just printed, and then you print your second layer of wiring. And then after that, then you can go to our roll-to-roll characterization line. This is where we can do hundreds of meters of inline characterization. This is a stop-and-go process where we have a flatbed of pins to measure the resistance of the particular metal that we've printed. In this particular use case, we did a daisy chain structure. You can see this is 1 repeat length on our printing line. So that's about our repeat length is about 40 centimeters by 30 centimeters. The cross direction is 30 centimeters. In the machine direction, the repeat length is 40 centimeters. And we did different sized via openings. In this study, we used this Melanex ST506, a particular high-grade polyethylene terephthalate. The ink we were using was this Asahi 411AW, and then there's the characteristics of the printing run. The main message here I want to give you is that depending on the screen parameters, the wet thickness of the ink, and if you fill or not the via hole, it'll have a different effect on your yield. So for instance, what does unfilled mean? Unfilled is without the additional via filling step. So you're just printing the circuitry on side A and side B, and then the via filling will just be from the printed traces. So it'll just inflow into the via. But if you want, you can have an additional via filling step with a thicker screen. So in this case, the filling layer was 125 microns to ensure that you're getting nice filling of the via. But if you notice, even without the via filling step and the thicker metallic trace printing, you were still able to fill the vias with really high yield. And looking at over 2,000 via pairs, we're at this over 100% yield. So that means that you don't really, unless you need a very thin printed trace, you don't necessarily need to do an additional via filling step. So here's some examples of what the via filling process looks like. You can see just from the diameter of the laser cut vias, you also have a conical structure of the via, and this was also observed in the cross sections. When we're looking at ITO PET, so this is indium tin oxide, we did an investigation with just a single layer of the ITO, and here you can see, so on the back side you'll have the ITO, and on the front side you have your daisy chain by the printed silver. And then, but here we also have the daisy chain on a double-sided ITO, so you can see that the vias were filled with silver, but the interconnections between the via holes is the ITO, so that's why it looks transparent. So you can see a closer view of this, and basically, in the case of the ITO, though, the via filling step was quite important, so that you're able to get really nice contact between that thin oxide layer and the via hole. Now for the printed PV module, we took the ITO substrates with the vias and the metal traces that were made in the previous runs, and we used that as an energy module platform with the so you can see your ITO here, your etched ITO, and then we would have the energy management IC. We also have an LED to show that the battery is being charged, and we also place a battery on this. So it's a multi-use platform. And in our case, we tested it both with organic photovoltaics and perovskite photovoltaics. With the OPV, you can see we used a P3HT-based active layer with both PCBM and ICBA. These are different fullerene derivatives, if you're not familiar. And then for the perovskite, this is quite a nice work. This is a flexible perovskite, and we actually won an award at the 2 years ago at the Munich LOPEC conference. It won the best demo award for this particular field. And of course, we can go into more detail if you're interested. But the point is that you have the point is just to show you the use case. That here you have your battery and your hybrid electronics, and then on the back side is your OPV. And of course, you might be wondering, of course, well, this isn't the product, but it's to show the use case of how this type of processing can be used. So I think it was a nice investigation. We did quite a lot more runs that I didn't share with you, looking at different screen types and ink types and things like this. But of course, that's some things that we keep internal at VTT. But I think there's a lot of future in this type of upscaling processes that I'm happy to share with you. So I think there's a lot of potential also for these double-sided systems and to upscale with this particular approach. And I'd like to thank some of the projects that I'm involved in, including, of course, this Astronics project and this PRAIN, this Photonics Research and Innovation, and some other funding authorities like Business Finland and the European Commission. So thank you very much for your time.